This problem gives us a function that tells us position. They want to know when the car is slowing down. So this can be tricky, but the big idea is you're slowing down if your velocity and your acceleration have different signs. Okay, so what we need to do is we need to find the velocity function, which is just the first derivative of the location function, the positional function. So it's negative 2t squared plus 6t plus 20. And we also need to know something about it, the acceleration, which is just the derivative of the velocity. And now we want to find when the velocity and the acceleration have different signs. Okay, so one thing we should look at first is a graph of the velocity, just a rough sketch. We don't have to get it exactly precise. It's quadratic, which means it's going to make a shape like this. It's going to cross the x-axis in two places. So this car is going forward between these two places, and it's backing up relative to the starting. Sorry, I should just say it's backing up to the left of this place and to the right of whatever this t value is. Okay, so the car is going to be slowing down wherever the acceleration is going to be negative. So at some point here, it's going to reach its maximum speed, and now the velocity is going down, right? Down, 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 down. So that whatever this location is here, that's going to be the key tipping point to when the car finally starts slowing down. Because before that, look, the velocity is, the car is backing up, backing up, backing up, backing up. Now the car is at zero for velocity. Now the car is going forward, going forward, going forward, and the velocity keeps increasing throughout all these places that I'm highlighting with my pencil. The velocity is increasing, so it's speeding up. It's when it reaches this peak, it's when the acceleration is zero, that it finally starts making a turning point and starts going down. So we need a couple things. We need to know what this t value is, and we need to know when the acceleration reaches that peak. What's the t value when we finally reach our peak speed and we start slowing down? So let's start with v of t. We want to find out where it crosses the x-axis. So we want to set that equal to 0. And then if you factor out the negative 2 from everything to keep the leading coefficient positive, and then continue factoring to help you solve, that's t minus 5, t plus 2. So we get two places at t equals negative 2 and t equals 5. So that's the place where the car starts going backwards again. Okay. Yeah, because then it starts speeding up just in reverse. Okay, from here on, this car is going forward at a faster and faster rate. Now we also want to find out where the acceleration, I'll do a quick sketch of the acceleration graph. It's linear, y-intercept of 6, going down by 4, so this is a rough sketch of the acceleration. We want to find out where the acceleration has different signs from the velocity function. Between t equals negative 2 and t equals 5, velocity is positive. Velocity is positive. For acceleration, velocity is positive up until wherever it crosses the x-axis. That's a nice quick equation to solve. We want to set it equal to 0. So look, everywhere to the left of whatever this place is, let's just solve it. That's t equals 3/2. So everywhere to the left of t equals 3/2, acceleration has the same sign as velocity. But everywhere to the right of t equals 3/2, acceleration is negative. Okay, so it's going to have an opposite sign in between these two values, t equals 3/2 and t equals 5. Acceleration is down in the negative section of the y-axis, but velocity is still in the positive section of the y-axis. So this is our interval. Okay, and that matches like the analysis we did at the beginning, that the velocity is going down. The car is slowing down between 3/2 and 5. So that's our answer for this problem, that interval.